All right. Yeah, so I think I had an error in my notation in the last part, so I'll just repeat it so everyone's on the same page. All right, so remember that we were looking at the stochastic gradient descent algorithm, or SGD. So we're starting at a point x0, and then we're doing a bunch of iterations where at each iteration we pick an example EI, and then we're applying the update xt plus 1 equals xt minus alpha times the gradient at fi of xt, right? So basically the key difference from gradient descent was that we're doing things with only with respect to specific examples. So then we were looking at mean estimation, and for mean estimation we have this trick that in this case the gradient is this, okay? And then we just wanted to see how well does gradient descent converge, or stochastic gradient descent converge, or what does it actually mean in the context of this of this specific problem. So then we can replace, like, our iteration xt plus 1 equals xt minus alpha gradient is literally this, right? Where I plugged in the value of the gradient here, and then by some magic trick I chose 1 over t as a learning rate. That sounds like a good idea in the case of this algorithm. This is something you would kind of need to do by hyperparameter tuning or something, but in this case there's a very good reason to pick 1 over t. And then with I'm taking this formula and replacing alpha t to be 1 over t, and then I get this. So I get xt plus 1 equals xt minus 1 over t xt. So this is basically this part over here with alpha t replaced, and then plus alpha t times EI, okay? So which is what I wrote here, and then notice that this thing over here is xt times t minus 1 over t plus EI over t, okay? So now I claim that this actually is going to devolve into something that's quite natural if I unroll the recursion. So I'm going to sort of guess that the right value for the recursion, let me actually rewrite this here. Like, basically I'm going to guess that the right basis of my induction is that xt is the sum for I equal 1 to t minus 1 of EI over t minus 1. So basically I'm going to guess that xt is my sort of the average over the last t minus 1 points that I've seen, okay? And so I use this as kind of my induction base, and then I can replace this inside my induction step. Let me rewrite this because it's a bit messy. So assuming that this is the case, I can replace this into the induction formula. So I'm going to get sum I equal 1 to t minus 1 EI over t minus 1 over t minus times t minus 1 over t. So these two become 1, and I get that this is going to be sum I equal 1 to t of EI over t, right? So basically I have built my induction step. So basically my tth, sort of the t plus first iterate is actually the average over all of the points I've seen so far. Okay, does this make sense? All right, so basically this gives us kind of a natural explanation for what gradient descent does in the very specific case of of this mean estimation problem. It basically gives us, like, if we parameterize it properly, it gives us the perfect sort of estimation based on t minus 1 points, based on the number of points we've seen so far. But it cannot be as good. Notice, like, we actually need a lot of iterations. We would need to go over the data set completely at least once in order to get the right mean, right? To obtain sort of the mean over all of the endpoints. Otherwise, we'll just have the mean over a randomly chosen subset of samples. Okay, good. So, I mean, more generally, what we can prove about gradient descent is basically the following. So, in general, SGD convergence theory says. So assuming that we start, let's say, at x0 equals 0, and we want to find, let's say, x star, which is the optimum of the function. Then what we will get, so we need to assume a few things about the function, because in general this is, I mean, the minimization of an arbitrary function is kind of intractable. If we could solve this, we could solve sort of NP hard problems. So we need to make some assumptions. So one would be something that's called, like, the function should be f should be L smooth. So what do I mean by this? So basically a function is called, not sure if I should go into full detail here. Okay, so let's say, so function f is L smooth if and only if we have that for any x, y in d dimensions, f of y less than or equal f of x plus gradient f of x transposed times y minus x plus L over 2 x minus y squared. Let me put in, this is the same here. So basically, what does this mean? If you recall the intuition that we had over here, right? So remember that we were saying, okay, we have the true function, which is this, and we had sort of the linear part of the function, which was this, around this point here, and then we wanted this kind of function rho to bound the quadratic difference between the function itself and the linear approximation over here. And what we're saying with the function being L smooth is that this gap, there exists a constant capital L, so that this gap between the function locally around the point y and the point x at which we're looking, at which we're looking at this, basically the difference between the function at y plus sort of minus the linear approximation here is going to be always upper bounded by a quadratic function whose main term is this L. Okay, so it says, okay, my function is always going to be upper bounded by some quadratic function. Okay, and then the other thing that we're going to need to assume is that f is L strongly convex. Okay, and what do I mean by this is that I mean that for all x, y in Rd, can you read this? It's better. Okay, well, it's a bit worse. F of y is going to be greater or equal f of x plus gradient f x transposed times y minus x plus L over 2 x minus y squared. So basically this is this is sort of the same thing as before, but kind of in reverse. So essentially we want to say our function, sort of the difference between the function and its linear approximation, which is this, should be always lower bounded by a quadratic with this parameter L. So the intuition, I mean, one intuition here would be that L always has to be greater than, like capital L always is greater or equal than small l. And we also have the condition number of a function which is usually like defined as rho or kappa, let's say, which is L over L. Okay, and this is this is kind of equivalent to the condition number you may have seen in linear systems. Okay, so I mean, I've kind of introduced these definitions so you kind of have them. We won't go into real analysis further than this, but there is one thing that I mean, I needed these definitions for a very specific reason in the context of sort of inconsistent SGD. So. More precisely, what we will be able to show, given these definitions, is that for an arbitrary L strongly convex and L smooth function, then SGD satisfies x t plus 1 minus x star squared. So basically, the iterate after a number of steps is going to be less than or equal to xt minus x star squared times 1 minus alpha t times L plus alpha t square sigma square, where sigma square is the gradient variance. Okay, so what does this actually mean in practice? So basically it means that if if we are sort of far away from the optimum, so this thing here is large, then sort of we will basically compress this difference by alpha t times L, which should be also something pretty large. However, we always kind of get pushed back by something that is proportional to the noise times the learning rate. So kind of always the game here is to control the learning rate so that the decrease in sort of length to the optimum is large enough so you're always making progress towards it, but it's not like basically your learning rate is not large enough so it actually blows up your variance term. So you can think about it as something like as follows. So let's assume we're kind of in this situation over here, and this would be kind of our variance. So basically, like initially, while our loss is large, we basically take these large steps. This would be because of minus alpha t L x t minus x star, right? And then once we are getting sort of in this region, once we get in here, basically we cannot guarantee that we're going to be closer to the optimum because of this variance term, which can sort of throw us around, right? We could just jump around in this ball. So the only thing that we can do here is to decrease the learning rate, which will also decrease this term. And this is why, like you remember in our gradient descent example, it was sufficient to take the learning rate of 1 for gradient descent, whereas for stochastic gradient descent, we actually had to take a learning rate of 1 over t. So it was kind of decreasing linearly with time. Okay? All right. So that's any questions about this? Yes?
But there is no sign of capital L in the error estimation, right?
You mean here?
Yeah.
Well, I mean, in order for this to hold, alpha t has to be at least 1 over L, or 1 over capital L. So in order to prove this, you will actually need, there is some kind of implicit conditions on how large the learning rate can be in order for this to hold. That's a very good point. Yeah.
So it's a lower bound on alpha.
Yeah, so basically, I'll put this here because this is important. So basically, for this to hold, need alpha t to be greater or equal 1 over L. Okay? I actually have a clean version of these notes, which I'll share so you can read them. I mean, I know my writing is a bit all over the place, but I have like a full version of this, which I'll share with you. So you don't need to stress too much about that. All right. So okay. So basically, this at this point we kind of know not a lot, but enough about HDD theory to actually go into the to try to understand why an asynchronous version or a communication compressed version of HDD could actually work. Okay. So let me try to go a bit deeper into the modeling, and then we can discuss. We can go back to the convergence theory. Okay. All right. So all right. So before this whole thing with the formulas happened, remember we were looking at distribution costs for HDD, and I claimed that we have two types of costs. One would be the gradient exchange part. Basically, this line is too long, and basically the other part is that I mean, basically we have to synchronize nodes at the end of every round. Okay, so basically we're wasting time because of synchronization and communication, and in fact, if you look at real executions, this is literally if you can you can profile via like an NVIDIA, like some kind of NVIDIA software. You can actually look at how the executions look like. They actually look a lot like this. So basically, you'll have gradient compute, gradient exchange, gradient update of parameters, and then you have this kind of part over here, which corresponds to everyone waiting for the slowest processor in order for them to be able to move to the next round. Okay? So basically, notice we're paying kind of two things here. This would be roughly the communication cost. Basically, during this green part, everything is basically being communicated. And then this is the synchronization, the waiting part. Okay? And we want to ideally reduce both of them. Okay? So basically, I mean, there are currently hundreds of methods which are supposed to mitigate versions of this. And you can have a look at, I mean, this survey is already a bit old. I think this is 2019. But this covers all, like a bunch of the methods up to that point. And then the other point here from the theoretical perspective is that each new scheme will need usually a pretty long and complex proof of convergence, which sort of attests its validity. Okay, and then today I'll try to give you an overview of an easier way to decide whether an algorithm works or not. Okay, so I put these formulas here, but we just discussed them. So I mean, this is just to remember what sort of sequential HDD guarantees, and we parallelize because we want to essentially reduce the variance in a short sequence of time as possible. Okay, and we have these trade-offs between lower variance due to parallelization and the cost of synchronization, which comes as communication or waiting times. Okay, so the key question is, imagine we want to tweak this iteration, such like for instance via quantization, or let's say we're running. I mean, I'm going to give you a simple example, which is like HDD with dropped messages in this case. And the point is, like, if, for instance, let's say we have HDD in a message passing system and some messages can get dropped, how do we model that? Okay? So, and how can we reason about its convergence? Okay? So again, let's look at our first example, the message passing system with a fully connected communication topology, except that we have an adversary which can drop or at least delay some of the messages. Okay, so basically in the first iteration, everyone sends a message to everyone, let's say. However, in the second iteration, let's say the adversary chooses to skip these two messages by node number 1 to nodes number 3 and 4, but all of the rest of the messages sort of get communicated. Okay? And I mean, even for instance, node number 1 could actually continue communicating in the next iteration. So we're not assuming crash faults for now. We're just assuming that some of the messages could be omitted. Okay? And if you try something like this, if you try HDD in a system like this, you'll see that this actually works just fine. Usually this is like dropping messages is usually not a problem. but analyzing this is pretty complicated. Okay, so I'll try to give you an example of how to reason through this. Okay? Questions about this?
You mean dropping messages up to some point?
Yes, I mean I assume that. Yes, I mean I will assume that there's like a bound f on the total number of dropped messages that can be sort of disappear, and that this bound is not very large. Let's say I don't know, up to square root of n or something like that. Okay.
What is a model that is close to practice here in terms of message losses or whatever?
I mean, in terms of specifically for message drops,
Whatever, just comment. I don't know.
probably something like something closer to these, let's say, eventual synchrony models would be more reasonable. So basically, you can assume n minus t messages are received by every node in every round, but let's say n t is greater than it's like 3/4 or something. Sorry, n minus t is greater than 3/4. But basically, the overlaps might be kind of arbitrary or something like that. I think that's kind of a reasonable example. This example is not as complicated. This example is more for people to kind of understand the modeling. But yes, let's say eventual synchrony would be a very reasonable practical model, which is why it appeared in the first place. Good. So basically, we're again in the HTD parallelization case, and note, like, remember that we were doing kind of sums at every iteration, at every step. But now we're asking, what if this sum is a partial sum? And what if different nodes see different partial sums? Right? This is kind of the key question here. Okay? So getting back to my previous slide, which was kind of explaining how HTD works, basically we have a bunch of iterations. In every iteration, each node I selects a sample EI uniformly at random from its distribution, computes and updates this kind of gradient, and then they sum their updates, let's say, and then each node I will update its model for the next iteration. Notice I've switched I from, the name for this from X to V for a very good reason, because basically they compute this update locally. This could be different at every node. And then they will update their view of the system based on the previous view minus learning rate times the gradient, okay? Where alpha is the learning rate, okay? Notice I've switched from model to view because each one of them could have a different view depending on which messages, which sort of dropped messages it actually saw, okay? So this might not be the same at every node, okay? So let's consider a specific round, okay? And I'm going to use two colors. So basically, I'm going to look at every node's messages, and I'm going to say, okay, the messages from node 1 and 4 were received by everyone. Therefore, I'm going to put them in blue. A message from node 3, let's say in this hypothetical round, was not received by anyone, so I'm going to put it in red. It got completely deleted. But then the message from node 2, it was received by some, but not all. So I can put it in this kind of, what's a good name for this? Cyan? Yeah. Something intermediate between red and blue. All right, good. So basically, notice we can have this kind of categorization of messages at a round, okay? And this categorization can give us different types of views for the nodes, right? So basically, if I look at the specific node I, it could actually, basically its iterate is VT minus learning rate times its own local view, which sort of has to select a subset. Certainly the ones in blue have to be in there, but for instance, the red one cannot be in there, and then whatever happens to this message is kind of decided by the adversary with respect to a specific node. Okay? Does this make sense? All right. So the basic analysis idea, which I'm going to follow in a couple of instances for the rest of this lecture, is basically we're going to define an auxiliary random variable, which I'm going to call x for sort of the true iterate in some sense, as opposed to the view, which is going to do the following. So basically what X is going to be doing is it's going to sum everything that was received by anyone. So basically I'm going to say like xt is going to be xt minus learning rate times, like for every iteration, like at every round, it will actually take into account all of the messages that are blue or cyan, right? But not the ones that are red because they're not seen by anyone. I mean, technically I could even take those into account, but then the adversary wouldn't use them. But technically, I mean, if we, maybe this would actually simplify things. So let's assume that everything that is generated by, if the node doesn't completely crash, then we will actually also take its gradient into account for that round, okay? And our bounds will still hold in that case. Okay, so our first goal will not be to show that each of the views converges, because that's going to be a bit tricky, but we want to show that this auxiliary variable converges, because this is kind of the best that the system could do up to some point in time, okay? So, I mean, this looks a lot like an SGD type of iteration. What is really the weird thing about this? Like there's like a single letter that's really annoying here. What makes this difficult? What makes this different from what we've seen so far? And I've sort of flashed some convergence rates at you. What is different in this iteration relative to all of the other iterations so far? We can go over symbols if you want. No, it was minus, it was there. Alpha was there. Sums were there. J's were there. This tilde is okay. So we got to V. So notice that in the standard SGD iteration, the gradients are taken with respect to the variable, like to the current iterate, right? However, in this weird iteration, we're taking gradients with respect to something else, right? So we're integrating gradients which are it's not even just the case that this is different from this. These things themselves are different from each other, right? So basically these nodes could be taking gradients at completely different points, and not completely different, but different, right? So this is problematic. You agree that this is problematic, right? This is really the key. Like this is the difference between a regular SGD iteration and this kind of inconsistent SGD iteration, which we're going to look at next. Okay? All right. So the key to analyzing this is actually in point 2. So our whole point and in some sense, our whole hope that this process will be converging has to stem from this fact that these node views cannot be too different from the general iteration, but also cannot be too different from each other. Because what are we missing? I mean, the whole difference between these nodes is maybe a single gradient update from one of them, or maybe two, but not arbitrarily large. Does this make sense? All right, so let's do an example of, then our job is in some sense simpler, because if we assume this framework, then all we need to sort of understand is how do the node views differ from xt and how do they differ between each other, okay? And assume that if you give me a bound for this, then I will be able to prove convergence to you for SGD.
But here again, it's like if you make assumptions about the power of the adversary, right?
Mm-hmm.
Stronger than what you described.
Yeah.
Right?
Yes, then you cannot do anything.
Exactly.
Yeah.
But what are these assumptions?
With respect to the power of the adversary, I mean,
Messages can be
yeah. So I'm assuming this is what I was going to get to next. But basically, I'm assuming an oblivious adversary, and which can drop f messages throughout the execution, and I assume f to be small in this specific example. Okay. So this is I think this is more or less complete. Yes.
If with weight near to each other, can we just pick any of the results?
Yes, yes. I mean, this is something. I don't think I'll go too deep into this, but yes, this is a good point. So basically, the point. His question is. I will reinterpret it as follows. So basically, imagine that I sort of wave my magic wand, and I tell you that this converges. Okay. But then the question is, I mean, how are we going to actually take a result from this set of machines? Because they don't. I mean, no one actually has this. Technically, no one might have this, right? So the question is, how do we pick the result? But basically, the proofs usually go by two stages. First, you prove that this converges, and then you prove that each individual VI will converge, but not at the same point. You actually might need to run it further a bit until the VIs get close enough to the previous XT. Does this make sense? So basically, we're showing some kind of convergence over time, where we first show that this converges, and then we show that the VIs actually have to kind of catch up to the XT over some additional time. Okay? That's a very good point. So, but this will allow you to maybe run a few more epochs and collect the result from any node, as you said. Okay. Yeah.
In this theorem, you don't have anything coming from the fault model?
I mean, this is, so this is, I should put sort of quotes around this. And this is the type of result that I would like to get. But the assumptions will kind of come in each individual case. But this is kind of my target, right? I want to say, okay, assuming a nicely convex smooth function and so on, I want to show that there exists a setting of the parameters which allow me to show that I'm eventually going to get there. But this is kind of where I would like to get. Okay, this is not a formal statement. This is just like a... Yeah. So this is what I would like to have for each one of these settings. Okay. So basically, our strategy will be the following. So we want to show that there exists. Like basically, we want to show that the distance between xt and each individual vt, which is kind of generated at a round, can be bounded in norm via something that depends on the learning rate times some kind of constant. And this constant could be, like, you'll see, it can be very, very different. Like the way this looks very, very different. So in the case of the fault model, f will be in here, okay? In case we're sparsifying, sort of the sparsification parameters will be in here. But the point, I mean, this is more, what I'm trying to describe is more of a proof strategy than the actual proof. But what we want to show is that these things can be bounded, and this bound is kind of something that's independent of time. So it's some kind of uniform bound, and then we will be able to work with this. And the nice thing is that we will see 3 different instances where this actually holds, this kind of bound actually holds. And it will be failures, asynchrony, and communication compression. But the proofs are going to be a bit different. Yep. All right. Good. So what we'll show, I mean, I'll show this only if there's time at the end. Basically, that if this is true, then the noise, this kind of noise factor, will actually get killed by the SGD process itself after some additional time. So we'll have to pay additional time in the running time in order to kill this difference between the ideal iterate and the sort of the local ones. Okay? So let's do a quick kind of cartoon example of this. How do we show that there exists such a B in the case of this kind of fault model? Okay, so we'll just do it for a single round. So remember, this means received by all, not received, partially received, received by all. Okay, and let's assume we are doing a single round. Okay, so then notice that if we have F failure, so what is V for a specific node in round 1? It's basically the sum over gradients, right? It's sort of modulo constants. It's actually the sum over gradients that it received in that round, correct? All right, so if we want to bound the difference between everything that was generated, which is the sum of all gradients, minus whatever this node has received, notice that we can just bound it modulo the number of gradients that were not received times their norm, correct? So then what we get is that the expected value of, like with respect to the randomness sort of chosen, of the actual iterate, which contains everything that was generated, minus the one that may have been received by any node at this step, is going to be at most alpha times m. These are sort of, this is the magnitude of the stuff that the node is missing. So it's alpha times m squared, because we have a square here, times the number of such rows that are missing from the view. So then this should hold, at least with respect to a single round. Does this make sense? I don't think I can erase that. All right.
Sorry, could you go over it again?
So basically, we want to bound this difference. But notice that, like, if we are, we're at a single round, right? So notice that this difference is actually, we can sum it over gradients, over individual received gradients, right? And notice that since we're at a single round, node I, like for the gradients that were produced and that the node has received, basically the contribution to this sum will be 0, because it will be gradient received minus, gradient produced minus gradient received. So it will be 0. Then we will actually have a sum of, basically a sum which will be squared, right? And then this we can upper bound, there's a 2 missing here, but this we can upper bound by basically 2 times the sort of the square of the individual components, right? So basically, so notice we will only pay for the components that are missing, but those components are in here. It's like they're summed squared, and they will be less than or equal to 2 times the individual square components. But that is literally like this is the number of components times the magnitude squared of each component, which will be alpha m squared. Yeah. No, because I'm actually looking at, so this corresponds to the, this corresponds to the magnitude squared, but we only have f of them. So this is the magnitude of each individual component that is missing squared, right?
But imagine a simple case.
Yeah.
Where it says only one dimension. And
Yeah.
we are steadily moving to the
Yes. Notice here we are. So let's actually assume your case. So basically, this is one entry that's missing, and this is another entry that's missing. So we will have basically here we will have a plus b squared, right? And here I'm saying this is less than or equal to a squared plus 2b squared.
But all steps if all steps are equal and we are missing n steps, then
No, I think you're missing the meaning of m. Like m is essentially m is an upper bound on the magnitude of any individual step. So it's
but if we are missing n steps, then square of difference must be n squared.
No, that's not quite the case. Notice that this doesn't quite matter in this case. Notice all I want to show here is that this is, in this simple example, this is upper bounded by a constant. Like this doesn't depend on time. This only depends on the number of failures, and the magnitude of every gradient, and the learning rate that we're using. So for my sort of framework to work, this would be sufficient. Even if this is even if this is square, I mean, this is not a square, but even if it were, this would not make any difference to sort of the general approach. Because remember, all we want to show is that we want to show something like this, where there's no t in here. But basically, I can sort of define my b however I want, as long as, so even if you somehow wanted to define b as m square f square, this would still be fine. You would get a worse convergence rate. We'll do another example in a lot more detail next. So let's maybe move past this.
Sorry, does f, the number of failures,
Yeah.
depends on time?
No, I mean, at least f, in my definition, f is like the upper bound over the entire execution of all of the messages that could be missing. So it doesn't depend on time. Over all steps. Yeah. So I'm willing to pay this basically at every step, and this should be fine. All right. So let's do another example in a bit more detail. Okay, so basically the motivation for what we're, remember Petra's question earlier, which was we want to reduce, essentially we want to do a different type of compression where we want to reduce the number of components which are sent between the nodes, the gradient components. And instead of doing, remember I was just using 2 colors before, what I'm going to say is that I'm going to choose colors that are very important and colors that are not very important. And then I'm going to only send those which are very important, and the other ones I will somehow not send. Okay, so this is gradient sparsification instead of quantization. Okay, so instead of reducing the number of bits that I use to generate illustrate every component, I will just say I will only send, let's say, large components, and the other ones I will throw away. Okay, this doesn't quite work, but there's a version of this that works. So basically, what we'll see is that with this, you can actually achieve very high compression rates, like close to 500x for actually reasonable tasks. And you can still get some kind of convergence guarantees, but it will be a bit more complicated. Okay? So, in practice, this is harder to use because you need to change the parameters of training in order to make this work. And you actually need to have some support for sparse types in your communication mechanism, which is not always obvious. Okay? So here's how it works. So basically, we fix an integer parameter k, and we only want to send the top k from each gradient vector in order ordered by absolute values of these components. And then the critical step is that we will not throw out the values that we don't send. We will actually accumulate them locally to a memory vector and add them into the next gradient. Okay, so how does this actually work? Let's assume I have a node here, which has all of these components. I'm going to take my k to be equal 2, so I take the top 2 values, which are what? In absolute value. Minus 0.3 and 0.3, just making sure people have not fallen asleep. So, okay, so basically we take the top 2, and then we send the top 2, okay? And notice that for k entries, I need to send k times 32 times log d bits. Why do I have this log d here?
Because you need to send the identity.
Yeah, I need to send the indices. Okay, very good. But however, notice that what I described earlier to Piotr were just this part, but this doesn't work. So what I need to do is I need to save the local error in here. So basically, this is going to be my error so far, which is all of the components I didn't send. And then I will actually add this or save this locally to an error vector. And in the next iteration, basically whenever, let's say in the next iteration I have another gradient coming here, I will add the error vector into here. Notice these will be different values. I will add the error vector into here and work with this again. Okay, this is basically, I'm going to do top 2 over that, and then transmit, and then save again, and do it again and again and again. Okay, so notice the important thing here is that nothing is really lost, but some things might be delayed for a very long time, and they will be averaged against new gradients that I generate in those components. Okay? All right, so this is called sparsification with memory, and this is very popular in like federated learning, for instance. Okay? So the key thing is that we're feeding back the error into the gradient. All right, so basically the key point here is that this is this is a different technique from what we've seen so far, specifically with respect to quantization, because recall that for quantization, in expectation, I was always doing the right thing. I could get like a noisier version, but like the expected value of the gradient I was sending was actually the correct value. But here, because I'm completely truncating some values, these values, I mean, this is like a different vector. I mean, its expected value is no longer the correct one at all, right? Which is why this memory mechanism is necessary. Does this make sense? Yes?
I think it's actually k multiplied by 32 plus probability because we just tried the numbers.
Ah, yes, sorry, you mean here. Yeah, that's right. Good. So, yeah, so basically, I mean, from the high level perspective, this is a great technique because we actually are using, I mean, our compression is about d over k log d. And if you pick k to be very, very small, this could be absolutely huge, right? So we could make, in some sense, we could make compression as high as we want it to be. However, I mean, now it really depends on whether it actually works or not. So experimentally, we know that we can get up to 400x compression with no accuracy loss. But this paper actually, I think, required 1.5 years of hyperparameter tuning. So basically, they really spent a long time to sort of work out the learning rate and momentum and so on to actually make this work. There is some theory. This is a paper we wrote a while ago. Yeah, as I said, this is not as general as it could be. Okay, so I promised you we would go over this in a bit more detail, so let's actually do that now. So basically, what is this exact algorithm that we're discussing here? So basically, we have, at every step, we're computing a gradient. This would be kind of a vector that we're getting. And notice this, I'm again using this kind of VT here because this is the gradient that the node is computing with respect to its own local view of whatever the model is. Okay? And I'm actually going to make things a bit easier because I'm going to assume that there's a single node that's kind of transmitting gradients to itself. So we're not going to assume two nodes, we're just going to assume a single one. And somehow this node wants to compress its own communication. So we're just going to kind of analyze a sequential version of this process instead of doing multiple nodes. Okay? So we have a single node. This allows me to ignore this kind of VTI here. There's a single node, node 1, which first computes the gradient based on its own local view, which only comprises compressed gradients. Okay? Then we apply the error accumulation from the previous round. Initially, this error is 0. So we do accumulated error is error plus alpha times the gradient of the previous, the current gradient that was computed. Then we do two things that could be done in parallel. So first, we update the error, which is the accumulator minus the top k of the accumulator, right? So basically, this is we're measuring how much error we have right now, and then we compress the update, which is basically top k of the accumulator. Okay? Does this sound like it matches what we had on the previous slide? All right, good. And then we're going to just apply the compressed update onto the node's local view. So basically, VT plus 1 is going to be VT minus CT. Okay? Does this sound reasonable? Okay, so in a distributed version, you would have two nodes which are kind of doing this. But just for simplicity, let's assume we're going to do this right now. Okay, so I mean, if you remember what we were discussing sort of just now, like what would be our goal here? What do we want to do? We want to prove that this converges, right? How are we going to do it? We need to find the constant. Very good. Yes. But before we find the constant, we need to define this kind of, there's no x so far, right? There's only v's. And we know v's are very complicated, and we cannot prove convergence of v's directly. So we should define an x, right? With the x would be, if you remember, this was the virtual iterate that we was supposed to be like easier to prove correct, right? So what would be how do we define this x? Remember, the intuition behind x was that x has to contain everything that was ever produced, right? Everything that we ever, every gradient that was produced needs to be stored somewhere, right? So so what's a good how do we define x? Yes, Alex?
We can define x as sum of all uncompressed gradients.
Yes, very good. So basically we can, as soon as something is produced, we put it into x. Okay? So let's do that. Okay, here I can illustrate how things are going maybe pictorially a bit more. So basically imagine this is the model dimension, this is the iteration number. What this iteration is doing is basically at every round, let's assume all of our values are positive, we basically select the largest entries and we drop the smaller ones into memory. Then the node generates something more, basically generates something more on top of every gradient. Notice here these were sent, so the error at these entries is 0. So this is kind of the new gradient entry. This is the accumulated, this is new, this is this is old, then this is accumulated, right? This starts from 0 and this is accumulated. Yeah, that's right. And now we take top k on top of this. This is why I put these in red. Okay? And then we do this again and again and again. And at our update is actually always consists of the largest entries from the accumulated gradient. Okay? All right, good. So, all right, so basically the iterate, it keeps track of these large elements that were updated, and the error keeps track of everything else. Okay? And nothing is ever lost, right? We've never zeroed out anything. Yes?
Even if x converges, why is the value it converges to reasonable? I mean, why it cannot be converged to some strange value that gives none?
You can prove that. You can prove that basically you can prove that x can get arbitrarily close to a minimizer of the actual loss function. That's how we prove this. Okay? All right. So basically, we need to introduce this virtual iterate, and we're going to define it the way Alex suggested. So basically, we're going to say at every iteration, we're going to define xt plus 1 as xt minus alpha gt of vt. Okay? And remember, we are again in this weird situation where, this looks like a normal enough HDD iteration. However, it is defined with respect to the view, and therefore it's kind of annoying. Like we cannot show direct guarantees for it. Okay? All right. So then, a reasonable question at this point is, okay, so we have essentially 3 major players in this algorithm. We have Vt, which with respect to which gradients are generated. We have the error, which is this weird thing that we're keeping around without knowing really why. And we have xt, which is this thing that I just introduced. Okay. So does anyone have any intuition? What is the relationship between these 3 players? We could try all combinations, but I think you're close enough that we need to give this some thought. Okay? So we know that, so you said x equals v plus e? Yeah, so it wasn't quite right, but you're close enough. So basically, we know that initially, I mean, I'm going to do this by induction so you can guess what it is. Basically, we know that initially v0 minus x0 is e0 because all of them start at 0. Okay? And then we can basically calculate this for t plus 1. So basically, we know that vt plus 1 minus xt plus 1 is, by definition of vt plus 1, is going to be vt minus xt plus alpha gt minus ct. This follows if you just follow, if you sort of use the definition of xt and the definition of like the definition of ct. Okay. Now we can take this one here, and yeah. So then we can take. Well, yeah. We notice that this thing here is literally minus et plus 1. Okay? So then we take the et and put it in here, and then we leave et plus 1 over here. So what we get is that like the first term is 0, and we're left with the second term, because like this happens by induction. So what we get is that vt plus 1 minus xt plus 1 is et plus 1. Okay? Yeah. CT is the actual update that's being applied. So CT is actually the top K of the accumulator. Okay. All right. So basically, we have this fairly nice relationship between these two. Okay, but notice that what we wanted to show was that this difference is upper bounded in terms of some constant stuff, right? And incidentally, this means that also our error should be bounded over time, which is kind of interesting if you think about it, right? And I mean, we know that vt plus 1 minus xt plus 1 is et plus 1, but this doesn't mean that this doesn't mean that this is necessarily bounded, right? So we need to show this here, okay? So in order to do this, we sort of derive this as follows. So basically, we know that this is an error, which means that it is a vector, this accumulated vector, minus the top k over a vector. However, by basic math, you can check this. Basically, the norm, the 2 norm of a vector minus its top k, is upper bounded by d minus k over d, where d is the dimension, times the norm of the vector itself. So here I replaced the accumulator with the gradient plus the previous error. Okay, this is just 2 steps in which, like, this is the norm of the accumulator, but this is also the definition of the accumulator. Okay, so notice that this suggests we should be doing some kind of induction or iteration, right? Because we can essentially split this out, and then we get d minus k times the norm of the current gradient plus d minus k over d times the norm of the previous error. But we can then start iterating this, right? So basically, the norm of the gradient at this step essentially gets multiplied with d minus k over d. Then the norm of the gradient at the previous step gets multiplied by d minus k over d squared. And then the next one gets multiplied by d minus k over d cubed, and so on and so forth, right? So we essentially get this formula over here, which means that, I mean, what does this kind of intuitively mean? Like, the older a component is that's being stored in this memory, the more it gets bashed. Like, the smaller it has to be in some sense. Like, the more it gets bashed with these d minus k factors. Okay? So, so basically, what we can assume now is that the norm of a single gradient is bounded, which is a standard assumption in these cases. So basically, we assume that the single gradient norm cannot be too large. And therefore, we will get, like, if we assume that the norm of this, like, if we assume that the norm here is upper bounded by, let's say, m squared, okay? Then we will actually get that this whole thing is going to be upper bounded by m squared times d minus k over d to the power I, which you can always sort of simplify to sort of the 2m squared d over k. Basically, this is standard. Yeah? Of what? But I'm using the triangle inequality here. I'm using the triangle inequality. There's no scalar product. So it's like it's norm. Okay, sorry. I see what you mean. There's again, it's the same trick as before. I'm missing a 2. No. So I'm missing a 2 factor here. So basically, this is like norm of a plus b square. This is less than or equal to 2 norm of a square plus 2 norm of b square. There's a 2 missings here. I'm sorry. Yeah. Sorry about that. You're right. Okay. So basically, yeah. So up to this error, I think. Okay. I need to fix. I'll fix this slide and upload a corrected version of it. However, hopefully you agree that up to constants, this is what we get is something like vt minus xt is upper bounded by alpha square m square d over k. Exponential? In what sense?
The way to have it now is to do the I, you see.
Yes, but I don't think this is a problem, right? Because you will get it here. And this says that k cannot be too small. But otherwise you will still get something that is subunit here. So this is this is a
I probably k is much smaller than
yeah.
so this initially was something a little bit less than 1, but now it's a little bit less than.
Yeah, so this derivation will only work if k is close to let's say like 3/4 or something like that. So basically this would still 2 times d minus k over d should still be something that is subunit, sub 1.
Yeah, but when they multiply it by you get something that's like 1.5.
This doesn't always hold, right?
So k should be at least a half.
Yeah, exactly. Yeah. So if k is more than a half, then this is fine. Yeah.
But still, when they put the 2 into this power, we will get something more than 1. And this like it won't converge.
you can set k to be
It's not about k, no matter how high you set it, when you
I see what you mean. Because it's like 2d okay, I see what you mean. There is a way of fixing this though.
Yes, there are not this.
maybe you pick k like more than half of t,
Yes.
then it decreases, but it seems like half the whole model is wrong.
So the reason why this looks so fishy is that it's like a heavily simplified derivation of like a much more complex one, which actually works for like much smaller k's. So I think I confused myself when rederiving this so I can fit it on a slide. But there exists like a version of like a much more complicated version of this, which would allow you to get sort of an end-to-end argument. So, I mean, I think in the interest of progress, we could assume that k is larger than d over 2, let's say, or even 3 over 4, even though this is kind of ridiculous from the sparsification perspective. But, I mean, in that case, we would be able to get like an upper bound. I'm happy to point you to, like, we can discuss the exact derivations which would allow you to get like non-trivial versions of k. Does that make sense? All right. Any other questions? All right. Good. So, I mean, up to this fudging here, notice we have obtained something that depends on the absolute value of, like, the upper bound on the gradient norm, d and k, and alpha, right? And remember, what we wanted to get was something like alpha squared times some b, right? And so this suggests that our b would be something like m squared d over k, right? All right. Good. So then the other trick here, the other thing to observe is that the larger, we kind of have the right sort of dependency between d and k, because like as k increases, our bound decreases. All right. Good. All right. So basically, okay, sorry. So basically, we have some. We based on this, we can actually prove that sparsification will, with error correction, converges, and one can obtain a variant of this, which actually gives you that the gradient norm will converge towards 0 as you increase the number of steps. So, and then the convergence rate will actually depend on the density parameter, this kind of k over d. This kind of guarantee with the gradient going towards 0 is the best one can obtain in the non-convex case, because we cannot prove that you can converge to a global minimizer. And this is somehow related to the proof of convergence for asynchronous SGD. And then, the key for convergence here, which was also kind of visible in the argument, is like we need to know how much gradient norm is actually transferred. So the top k is, like, for a given sparsity, actually the top k is kind of the optimal choice with respect to that sparsity. Okay, so basically taking notice it wouldn't make sense to pick. If you have to send k values, this suggests like the norm maximizing choice of k values is actually the top k. Okay, so that's sort of why people have also kind of gravitated towards this choice in practice. All right, good. So then, sorry. All right, so maybe the last example that I want to give you is that of asynchronous SGD. I guess I still have, Piotr, I still have 15 minutes for this? Yep. All right, so let's return to the example of sort of SGD in asynchronous shared memory. So remember that this, I'll try to do it from scratch because I actually had some questions about this in the break. So basically, we have P threads which are running SGD, but now it's on a shared model. So we're going to assume that the model M has all of these components. And then basically, we are again in the similar setup where nodes nodes want to apply SGD. And in order to do this, they essentially scan this model. So they obtain, you can assume that they go and read the first component, read the second component, read the third, and so on, when going up to the dth one. So they get like a collect view of the model. And then the model gets, then they compute their gradient locally based on this view. And then the model is updated using atomic operations. So we can assume that these happen via fetch and add. let's say, on the corresponding location. So basically, the model, the node has generated a specific entry in a in the gradient, and then performs fetch and add onto this entry in order to sort of update it, and then sort of does this for all of the other ones. Okay? Does this make any sense?
So which process does the things on that?
Sorry?
Which process does
All of them. That's the magic of it. All of them will do fetch and add asynchronously.
in all positions?
I mean, in theory, yes.
But then they are gonna add the same error.
Not really, because the gradients are actually, they compute gradients with respect to distinct samples. So they're not going to overwrite each other. Okay, does this make sense? Yeah.
So each processor writes to its own location.
No. They basically, in the generalized version of this, every processor writes to every location.
So this is why you need fetch and add.
Yes. Yeah, that's right. Otherwise, it wouldn't be necessary. I mean, you can analyze like the single writer multi-reader version of this as well, but it's, let's say, less interesting. Okay. All right. So basically, I mean, but notice it could be the original sort of Hogwild analysis analyzed this in the setting where I mean, there are setups where the data set is sparse, and therefore the threads will actually only update a specific subset of features. So basically, each of these corresponds to like the weight of a specific feature, and then each processor will actually only update a subset of the features, which is kind of a simplifying assumption. I mean, I'll show you where it sort of where it enters the bound. Okay. So all right. So we can assume this setup. I mean, we can assume that everyone writes to everything and reads everything, and the question would be, does it still converge under inconsistent iterations? And I mean, you know the story so far. We have to look for the bound B. Okay, so basically, like instead of doing single reads, we're doing kind of vector reads and vector writes here. Okay, and the writes, I'm assuming, happen via fetch and add on the updated version of sort of vector X or vector M, however you want to call it. Okay, so like one observation is that no one actually, I mean, unless they use a snapshot, these processors sort of may see inconsistent, like completely inconsistent views of M, right? And then writes are not atomic. So therefore, a single processor might actually sort of be in the process of writing to the vector while being sort of preempted by the adversary, right? And then, so in order to make any sense of this, we'll actually assume an ordering of the iteration. So whenever I say T, I'm going to assume that I'm going to order them by the linearization point of the first write. Basically, so this means that whenever the processor starts writing, it means that it has already obtained its view, and it has already generated the gradient based on this view. So because that's kind of a precondition in its own control flow to writing the first sort of entry. Okay? So based on this quick formalism, what do we need to define? I mean, we need to find B. For this, we need to define X. Very good. Thank you. Good. So how do we define X? It should be, thank you very much. So it should be the sum of all values that were ever generated. Okay? So basically, let's take this example where in this example, I'm gonna put in red everything that was already written. Okay? And then in this is sort of the everything that was kind of already written in the current sort of loop of the processor who's doing the writing. So what this means is that the way to read this graph would be something like this means that there was an iteration here. So imagine we started at 0, sort of 0 is the base. And then in the first iteration, we have sort of all of, this processor wrote all of these gradient values, okay? Or not wrote, but sort of added. This would be sort of the value of the entry at the point where the processor, after the point where the processor did the fetch and add, okay? And then we have another processor which sort of did the fetch and add, which resulted in this. But the processor was not able to progress past this point, so it didn't do the fetch and add here. Like it didn't apply the fetch and add with respect to 8.3, and it didn't do the fetch and add with respect to 11.7. So basically, this would be an entry that's sort of hanging. It's kind of a gradient entry that was generated by this processor, and it's kind of hanging in the air, waiting to be applied. Okay, so if this processor gets scheduled next, it will add 8.3 onto the current value of this register. However, the current value of this register is not 15.2. It is actually 15.2 plus 2.2, right? Because there's another processor which already started, which is already here. Okay, so then so let's assume that this one progresses here. Then it would actually add in its second step, it would add 11.7 to 14.2 and so on. Okay, does this make sense? Okay.
So what you saw there is these are the shared variables or the local variables that the process.
These are the local. So basically, yes, these are the local variables. Yes.
Then when you make them red,
It means that they have already been updated.
okay.
They have already been flushed, so to say, into memory. Okay.
And the red values are what they flashed or what.
Yes. What they either, if they're red, then if they are red, then they're already flushed, and if they're black, it means that they will be flushed. Yeah. All right. So good. So now, what is X? Yes. So I mean, X is actually, yes. I mean, I guess someone could just repeat the same thing over and over again. So basically, notice X is not so hard to define. Like if I put someone in here, it means it has already been kind of linearized. Its first write has been linearized. So technically, you get into X, like basically everything that you have generated gets added into X. So X would be the sum over all rows, like the sum over sort of gradient values over all rows. Okay? Does this make any sense? I mean, so my point is, like, notice that in all of our definitions so far, X was actually just the sum over all gradients that were generated, that we're taking into account. So X is not particularly hard to define. It's actually V and the difference between V and X that's kind of a bit hard to define, right? So now, what is V? Like, let's say we have a new processor that comes in here and wants to read the model M. What would this processor see? I mean, in some sense, you'll already answer this question for us. What would the processor see? It would see the sum over red values across every column, right? It would have to see all of them here, this and this, but not this, and this, right? Right? Yes, no, maybe. Yeah, I mean, these are, sorry?
Only if you stop the writes, but writes are coming in.
Yeah. I mean, I'm assuming that I'm assuming that this is I'm assuming that this is like a let's say a snapshot at this point in time, because it could be much messier because these guys could read while the other guys writes and so on. Yeah, that's a very good point. Yeah. Okay, good. So then, okay. So then the question is, how do we need to bound xt minus vt. So in this case, what is xt minus vt? It's basically the sum. I mean, we need to bound this in 2 norm, which actually is kind of complicated. But basically, this would be the sum over all possible black values that we could have this in here, right? And what we know, the only thing we know in this model, which is kind of the model given to us by Hogwell, is this tau max, which is how far behind a specific processor could be. Basically, how far behind we could have like a black value while there's still like a lot of red values above it, which would be sort of the maximum delay of a specific processor that maybe hasn't finished writing. Okay? So does anyone of you maybe have some intuition as to how large that could be? No, unfortunately, yeah, that's the problem. Because basically, no, yeah, it has to be tau, and it cannot just be the number of processes. Because notice we could have like a black value which is like under a huge pile of red values. Yeah. No, yeah, no, I mean, it's fine. As you can see, I'm also thinking through my own slides, so it's certainly fine for the audience to do this. But the point, my point is that our upper bound cannot only depend on n, it also has to depend on the maximum delay. Because of this, yeah, so you would have tau, yeah?
One process
yeah.
Did all the job and all other waiting.
Yeah.
And they can wait for tau steps. So
yeah.
Number of process minus 1 times
yeah.
tau.
Something, I think we can eliminate the n. So I mean, I think, so if we define tau to be the maximum number of previous updates that the scan might miss, which is basically the maximum interval contention of any single operation, basically then we don't have the n, we don't need the n anymore. It's basically kind of the maximum depth at which we could have a black value. And I'll give you the update here. I knew I wouldn't get to sort of cover it, but basically the b square, the b value here is actually tau max, which is kind of what was your intuition, times how large, basically how large the 2 norm of a single, I mean, notice you could actually have like almost a full row in this situation. So basically you would have the sum of squared values over that row, which is actually d times m square. So basically, I mean, it's the bound is pretty bad because it depends on tau max, like the maximum sort of interval contention, d, the dimension of the model, and m, which is kind of the largest value of the sort of largest gradient. And yeah, I mean, we can discuss kind of intuitive reasons for why these parameters are there, but this is close to the best known bound. Yeah.
Does this assume that this new process will perform a scan and not a collect? Or it's going to be the same even if it performs a collect?
I think the problem is that you could have, like, basically, you could, it's actually right. This bad process is kind of, this is, I mean, in some sense, the easiest way to think about it is to recall the example I showed on the previous set of slides, where you have a process that gets frozen on its first iteration. So it has a huge gradient that's actually not very good for us. Basically, we've made a lot of progress past this point. But because that, I mean, basically that process could be stopped after, let's say, its first point, let's say like it's stopped here, we have a pile of red stuff. But basically what this process will do next, if everyone else gets frozen, it just starts writing its updates, starts doing fetch and adds. And in this case, it can throw us out a lot. Like its updates are very large, very noisy, and completely useless. But at least in this asynchronous model, this is the best we can do. Now, there's a lot of work in this area which tries to do things, I mean, basically tries to tweak the scheme so you don't have this worst case lower bound. So for instance, you could read off a count, like an iteration counter, and dampen your update by 1 over the iteration counter or something like that, how far you are or something like that. And certainly you can improve this, but this is kind of not my point for the lecture. Yeah. All right. Good. So what we get is that you again, like under like a lot of analytic assumptions, then you can actually get a similar type of guarantee for this. The convergence will depend linearly on d and tau max. You can actually reduce this by some tricks to something like d times square root of tau max n, just by using standard bounds on interval contention. This is like a simple trick. I'll actually, I mean, with the stuff that I've given you so far, I'll share with you some lecture notes where you can actually go over this and rederive the bounds yourself in case you want. All right, so let me see. So yeah, I guess I'll wrap up here. So basically, I mean, what I wanted to show, like to talk about today, is basically mapping various inconsistent distributed settings to the same setup. Basically, a setup in which we have a sort of like processors get like a partial view of the system and have to compute their gradient based on this partial view. So then we define this kind of true iterate, which includes everything that's generated in the system, and we just need to bound the difference between this true iterate and the approximate one. I gave you I mean, admittedly, a sloppy way of deriving such bounds B. I'm happy to share the actual formal sort of derivations with you afterwards. And yeah, I mean, again, you've seen this in the convex case. There's like a lot of theory to how to do this in the non-convex case and so on. So if you're interested in this kind of stuff, I'm very happy to talk about it. So yeah, I mean, generally, I guess I wanted to say that like these topics are kind of critical for distributed machine learning. So like some of the very largest models, they're actually trained in an asynchronous communication compressed way. So you do need this kind of trickery, maybe not to the level of sort of worst case bounds that we've discussed, but basically you do need notions like this to actually train very, very large models. And then it's nice that we have a burgeoning theory of convergence for these types of algorithms, communication efficient, but also asynchronous versions of SGD. And then for those of you who are maybe interested in doing research in this area, I think it's really a wide open area. So there's like hot topics like federated learning, which applies a lot of this communication reduction stuff, and then Byzantine resilient learning, where I think there's a recent book out by Rashid Gerawi and co-authors. And then there's also some interesting stuff I can sort of share separately on actually doing model parallel training. So in a setup where the model itself has to be split among multiple nodes. So therefore, this creates like a lot of additional issues and so on. All right, so I'll stop here and take any more questions if there are.
Thank you very much.